Let me show you something cool. So what just happened here? This power supply created a current, a flow of electrons traveled over here to a capacitor. Now a capacitor is two metal plates in an insulating oil. Charge can't flow through the oil from one plate to another, so it builds up on one of the plates, charging it negatively. The other plate is left with a positive charge. This creates a potential difference, some voltage across the capacitor. Potential difference is kind of like potential energy. The more charge you build up between the plates, the more voltage you have, and the more energy you have stored in the capacitor. I've been charging this capacitor for about 20 minutes. And it's charged up now to about 3,000 volts. From this potential difference, you can calculate that there's 450 joules of energy in this capacitor. So that energy just sits there until I flip this switch. When I do that, I'm completing a circuit where an iron wire connects the two plates of the capacitor. Imagine destroying the Hoover Dam. Huge water flow. It's the same thing here. Electrons will rush from the negative plate through the iron wire to the positive plate, and the wire can't handle all that current. Now, the voltage in the capacitor after it's been charged up is going to be really high. That means there's a lot of energy that's going to flow through the iron wire. Because the wire has some resistance and is very thin, it can't handle all this energy. As the current flows through it, some energy dissipates out as heat, but there's just so much heat that the wire explodes. Now the wire actually explodes before all the charge can finish leaving the capacitor. So I'm going to take this copper bar and touch it to the two capacitor plates so it can finish discharging. Now the thick copper bar has a much bigger cross-sectional area than the thin iron wire and has less resistance. So it dissipated the energy better and didn't explode.